Dear friends, good afternoon. I welcome you all. The Department of Physics of our college is organizing the webinar on low-dimensional physics, a new paradigm. This is one of its kind, adding to the series of webinars being organized by our college. We are fortunate enough to get one of the renowned resource persons, Dr. Ramesh Thamankar, as a resource person for this webinar. Participants, please note, you can type your queries in the chat box, and we'll be taking that at the end of the presentation. After the webinar, everyone will be getting a e-certificate on the submission of the feedback, for which we'll be sharing the link in the chat box itself. Once the webinar is done. Now I request Dr. Vincent Krasa, the head of the department, to introduce the honorable speaker.
Good afternoon to everyone. It is my pleasure to introduce the speaker of today's faculty development program and a good friend of mine, Dr. Ramesh Thamankar, to you all. Dr. Ramesh Thamankar completed his MSc from Mangalore University in the year 1994, and later in the year 1996 to 97, he was a research assistant at Material Research Center, Indian Institute of Science, Bangalore. From there, he went to do his MTech program in material engineering at NIT Surathkal. And after completion of MTech, he did his PhD in structure and magnetism of ultra-thin three-dimensional light films at Institute for Experimental Physics, Free University, Germany. Later in the year 2004 to 2006, he did his postdoctoral fellow at the Department of Physics, University of California, worked on spin transport through carbon nanotubes. Then he continued his postdoctoral fellowship at the Max Planck Institute for Microstructural Physics, Germany. And then he was a scientist at the Institute of Material Research and Engineering, Singapore. Also, the senior research assistant at Singapore University of Technology and Design. Since last 3 years, he is working as associate professor in the Department of Physics, School of Advanced Sciences, Vellore Institute of Technology, Vellore. A warm welcome to Dr. Ramesh Thamankar. Also, welcome to all the participants. Now I request Dr. Thamankar kindly to do the presentation in low dimension physics, a new paradigm. Over to Dr. Ramesh.
Hello. Good evening, everybody. Can you hear me?
Yes, sir, you are audible.
Okay. So thank you so much, Professor Krasta, for inviting me for this seminar or invited lecture. First of all, my apologies to all the participants for not able to come online in the morning. Somehow we have fixed the error, and it's good that we have time to spend time to discuss science rather than other topics. So, as the moderator told, I'm Ramesh. I'm currently working as associate professor in Vellore University of Vellore, you can say, or VIT Vellore. And I will be talking on physics at low dimensions, which is my favorite subject of study and research since a couple of decades. And I'll give you a broad overview about things happening in this field of research. And so I'll share this screen. So this is okay, right? Hello?
Yes, Dr. Ramesh.
Okay, thank you. So all the development, science and development over the period of last 5 decades, we have termed it as technology driving the society. So that means every day newer and newer devices are coming in the society or in the market, and we need more. Now I can rearrange or reorganize this question or statement. Technology drives the society to what drives the technology. Okay, so this is the question we are going to ask, and we from the field of fundamental science, we always know that the technology is the product of extensive science and development, science and research happening in the laboratories. So that's what my question is: what drives the technology? So I really like this cartoon, which actually tells you the whole story. The technology is carried out or carried by the scientific development. So uh, it says that science drives the technology by making new technology possible through scientific breakthroughs. So today what we will do is we will just discuss some scientific contents, scientific topics, and especially since my interest is in low dimensions, I will concentrate only on low dimensions. So why worry about low dimensional physics or physics at low dimension? So first of all, it is interesting. The science at small scale is very, very exciting, interesting, because you are in the regime where you're talking about single atoms, single molecules, or cluster of atoms, or molecules, or nanoparticles. The first problem or first thing you need to do is, how do I see this matter or matter at the nanoscale, or entity in the nanoscale, or few atoms or single atoms? And once you see this matter at a small scale, then is it possible to control them? Control them in such a way that I can take this matter from one place to another, so that I can design a newer and newer electronic devices, and understand the science along that line, and probably design a newer and better devices. Now, when you start working on this small scale, what really happens is the number of atoms you are considering is extremely small. Okay, when I say extremely small, small compared to the bulk structures, what you see on this. So always the concepts of dimensionalities come into picture, whether you are talking about two dimension, whether you are talking about one dimension or zero dimension or single atom. Okay, the crystallography is completely different. So the completely different in the sense that crystallography is even simpler compared to the bulk systems, and the electrical properties and the magnetic properties show up in a completely different way. That means we need to have a newer definition for electronic transport or electrical transport. Okay, so this is the problems at the science level. But there are another set of problems in the engineering level. That means, how do you use these nanomaterials for a useful purpose? Okay, so do you have a newer regime of electronics, like when you're considering atoms of 10 atoms or 50 atoms, for example? Does it behave exactly like the bulk electronics and optics also? You can think that you are not in the bulk regime of electronics, but rather you are in the regime of nanoelectronics or atomic scale electronics. There are huge applications from the sides, I mean, in the direction of biomedical application, like drug delivery, for example. Better sensors you can design, and faster switching electronic devices you can design. And you can also design some fabric, which is adjusting to the atmospheric temperature and humidity. So all these are kind of applications, and these are some of the applications which are currently worked on, and it might take one more decade to get things in the market. Okay? So these are the things which we are interested in. So my part is on the left side, understand science at the small scale, and I do have some ideas about applying them to useful applications. The whole thing drives from our uh, 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 what we want to achieve in few years. We always go to this Intel company Intel, and we always check what is their roadmap for a few years or let's say a decade. So here is a roadmap of it's a fairly older roadmap of Intel. So we are at 2020, and look at the kind of development they have made across 1 or 2 decades. So in 2007 or 9, for example, they were in the stages where they could manufacture electronic devices of the size 45 nanometers, for example. Okay, and 2009 they were manufacturing devices of about 32 nanometers. We call this as nodes. Okay, so you can simply think node as distance between the source and drain in a transistor, okay, or a diode, for example. So these were in the manufacturing state, and I know now currently we are in the 14 nanometer form. And look what they are trying to do in future, or currently they are doing. They want to design the instruments, they want to design the electronic devices using one single carbon tube, which is of 1 nanometer diameter, let's say 1 to 5 nanometers. They want to design a newer electronic devices, sensors, or a switch, for example, using one atomic layer of graphene. They want to design the devices with the nanowires, which are about 5 nanometers in diameter. So obviously our devices are shrinking. So that means we need a newer and newer definition for understanding the physics at this scale. Okay. So okay, so when you reduce the size, what really happens in the devices? For example, if you take 22 nanometer node, that means if the source and drain distance is about 22 nanometers node. In normal silicon electronics, you have about 160 to 190 electrons to consider. So that means all the dynamics of this electronic device is with respect to those number of electrons. And come to 5 nanometer node, that's the target of Intel, for example. That means you have only 10 to 15 electrons. So your electronic device, your transistor, your switch is working with some number of electrons, which are now in tens. Okay, 10 electrons. Can you believe this? 10 electrons in your devices. So that means you have to understand how these 10 electrons behave. Even a single defect in the channel, okay, source and drain, you can imagine, and you have one single defect, which is external defect. These 10 to 11 electrons are scattered by that single defect. So that means you have to have extremely carefully optimized device manufacturing, and you need to know better about what these electrons do at that small scale. Okay. So the idea of the small scale, in the sense of number of electrons or number of atoms, is not that new. Richard Feynman, one of my favorite professors in physics, he had already told in 1950s, 1959, that the principle of physics, as far as I can see, do not speak against maneuvering the things atom by atom. This is, remember, we did not even have a computer. I mean, the computer what we have now. This was time of counting machines, and he had already proposed that the manipulating or maneuvering atoms by atom is not a big deal, and not a big deal in the sense it will not violate any principle of physics. It is not an attempt to violate any laws of physics. It is something that can be done, but in practice it has not been done because we are too big. We humans are too big to manipulate single atoms. So we need special techniques, special instruments to do all these electronics at small scale. Okay, so all the scientific development and technological development, what we talk and we experience day-to-day life, is because of some people who really try to understand nature at this scale. Some of them I'm actually pointing here. In 1900, Max Planck solved the mystery of what is light, and he said that the electromagnetic wave, which was already established picture of light, should be considered, or should be treated as a stream of photons, the particles, Now, these particles are not like classical particles. Please remember that whenever we say a word, particle means people might think that this can be divided or broken into pieces. But this particle, what Planck hypothesized, is a particle which is indivisible. You can have integral multiple of these particles, like 10 photons, 10 quantas. There is nothing like half quanta or 1/4 of a quanta. So this is one picture of a light. And in 1905, we have Albert Einstein giving us one of the beautiful theory of relativity, special theory of relativity. And in 1913, we had this wonderful idea of planetary model of atomic systems, where electron is revolving around the nucleus with no energy loss. And so there was a lot of refutation and agreement with respect to this model of Bohr. And in 1922, both of them got Nobel Prize. And I hear the story that Einstein did not go to receive his Nobel Prize, while Bohr went to receive the Nobel Prize on that year. It would have been nice to see both of them together and discussing about science or atomic scale or the principle of nature during the presentation. In 1920s, there were some people who thought that if Einstein and Planck can tell us that the electromagnetic wave can be quantized, that means electromagnetic wave can be idealized or seen as a stream of particles, then all the matter particles that we already have as electrons, protons, and neutrons should be envisioned as electromagnetic wave or wave cap or associated with a wave cap. Okay? So this is the dilemma we had over 3 decades, where we did not know, or even now we do not know, what is actually light. When I say I do not know, means I know it is a stream of photons, provided I do certain experiment which satisfies that principle. I do certain other experiment to prove that it is a wave. I get some wave character. So that means I agree on both these facts. And why does this light behave like this? And nobody knows. And similarly, in the case of matter particles, for example, electrons, or protons, or neutrons, or even many atomic systems like molecules, for example, you can associate that with the wave character. Okay? So that means if you are trying to see the electron, for example, it is not possible because it might behave as a wave. So the idea of technological development comes from all the scientific advancement we had for these 3 decades. And the idea of de Broglie, for example, was to say that the electron, which is under perpetual motion inside an atom, should be assigned with a wave character. Okay, so that wave character, which is defined by a particular wavelength, is inversely proportional to the velocity with which it is traveling. Okay, and we call this as de Broglie wavelength, and it can be written something like this: h by mv. Why I am emphasizing these things, these simple things, which we might have already learned in back in 12th or first years of BTech or undergraduate studies, because the devices or the dynamics of either photon or electron, what we see in the devices, is primarily because of these characters. Okay, so if you have a device where you apply an electric field, for example, then the wave character associated with the electrons in that particular device can be written something like this. Now you can ask why I cannot see the wave character of a bigger particle, human being, for example. Now please see that in the numerator there is this Planck's constant, which is 10 to the minus 34 Joule second, which is extremely small. So that is the reason why we cannot see the wave character of a human being, for example. Would have been nice to see the wave character of a human being under this principle, but fortunately we do not see. Okay, that means we are non-relativistic particles, and the velocity with which we can move is extremely small, compared to the velocity of light. So our wave character, or wavelength associated with us is so small that it is not measured. Okay? So that means the bottom line is all these fundamental particles, mostly electrons, because we are trying to understand physics at small scale, and most of the time electrons are involved in this. So electrons should be associated with a wave character. So how do we write this wave character? Wave character means it has to be a wave function or mathematical function. Okay, so this is a very strange character. Whoever is not from physics background, please pardon me using these strange characters here, but please assume that this is a wave character associated for the electrons. Okay, and since you already know that electrons are not stationary, they are dynamic, so there has to be some equation which defines its dynamics. So the Schrodinger equation, which is one of the very famous equations in the world history of physics, which actually tells us how this electron behaves, how this electron is moving. Okay, so this is kinetic energy part in terms of the wave function. This is the potential energy, and this is the total energy in terms of the wave function. So please remember that for any problem in the nanoscale or atomic scale, the first thing we do is and we solve. Okay. Okay. So this is what we have got till now. You have light, which was considered as an electromagnetic wave, can be considered as photons, and the energy of a photon is directly proportional to the frequency, and the momentum is given by h2 by c, the velocity which it is traveling. And the term which we use is quantum. Okay. For electrons, for example, which we know it has a mass and it has a velocity, so we can assign a momentum for that, and we can assign energy p square by 2 for that, and correspondingly we can assign a wave character written by this particular equation. This is a general equation for a wave function for a particle. Okay? If there are students in the audience, we actually can prove that it has to be something like this. Okay, you cannot use a simple sine wave for a wave function. You cannot use a simple, say, cosine function for a wave function, but it has to be a complex quantity. Okay, so there are certain rules which it has to follow, etc., etc. Okay, so now if you assign a wave function, that means this function should tell me that there is this electron which is moving with certain velocity, and if it is a electronic device, that means this electron is moving with certain velocity from source to drain, let's say, that constitutes a current. So that means the only input parameter which you had was wave function, now should give you all the information about its momentum, its energy, its velocity for that matter, or the amount of current it is actually giving in the circuit. Okay? So that is why when we select this wave function, we will be extremely careful to define this wave function. So the wave functions can be real functions and or complex functions. So this has to give us the probability of finding the particle, because now we're talking about all these things in terms of wave character. We will not be able to specifically tell that electron is here or there. We can just say that this is highly probable that electron is here. It is highly probable that electron is not here. So that means we will talk about the electrons and fundamental particles in terms of the probabilities. And the overall probability has to be 1, because you know that there are electrons exist there. So overall probability should be 1. So you define the function. The probability is given by the square of this function. So you choose the mathematical function which satisfies certain rules in such a way that the square of this function will give you the probability of this electron at that particular space. Okay, and obviously the overall probability should be 1, because you are defining or you're explaining a physically existing system. So these are the conditions this wave function has to satisfy. Now, what is the implication of assigning a wave function for the electron? Okay, so I will just go slightly ahead. Now, when will you say, so that's the question we will ask in a few slides now. Okay, what are the implications of assigning a wave function? Now, since our discussion today is about low-dimensional materials or low-dimensional physics, now the fundamental question you might ask, when do you say a material is low-dimensional? Okay, so there are few definitions for low dimensions. Now, when the dimension of the material is equal to the light what you use to analyze. Okay, that is one definition. For example, use optical light generally. This optical light has wavelength regime from 400 nanometers to 700 nanometers. So that means if the size of the object what you're trying to understand is of the order of the wavelength of this light, so you can say that it is in the lower range. Okay, that's one definition for lower range. The another one is if the dimension of the particle or a system or the material that you are preparing or designing is of the order of the Broglie wavelength. Okay, as I said, every system has to be defined with the wave function, wave character, and that wave character is given by h divided by the momentum of that particle. So that means if your system design or material prepared or a nanowire prepared is, or a nanoparticle prepared is of the order of de Broglie wavelength, then you say that it is in lower dimension. Okay, it is not a bulk material. Similarly, in the case of semiconductors, for example, if the size of the semiconductor dot or semiconductor particle is of the order of its excitonal radius, RB, written as RB, then you will say that it is in the lower dimension. Okay, so there are various reasons why you have multiple definitions, and the most common definition what we learn in the undergrad or classes is that in the case of lower dimension you have extremely high neighbours. Okay, for example, I just give you a schematic representation of how we define this lower dimension. For example, I just put some 300 dots here, regularly arranged. This is what a three-dimensional crystal represents. Regularly arranged atomic sites, and atoms are situated in that sites. So this is a bulk crystal, and if you count the atoms on the surface here, and they are about 54. Okay, so in the case of a bulk material, the number of atoms on the surface to the number of atoms in the bulk is about half, let's say 50%. Okay, now I consider a reference atom here, and I reduce this bulk material into a small particle, quantum particle, say a nanodot or a nanoparticle. Now, if you count the number of atoms inside here, okay, so that will be about 23 on the surface and 65 overall atoms. So that means it's almost about 1/3. So from half, or sorry, 1/6 to 1/3. And again, if you reduce the size of this nanoparticle to still smaller dimensions, what you see is the number of atoms on the surface and number of atoms overall in that is about 50%. So that means the surface atoms to the volume atoms, the number of surface atoms to the number of atoms in the whole volume is actually changing. So this is the fundamental definition we give. So the ratio of surface atoms to the atoms in the volume, which is actually increasing. So as you increase, you will see that the material goes to the lower dimension. So you have many definitions for defining the material in the lower dimension. Okay, so let's go back to the function. Okay, so that means we have satisfied. So we have satisfied our wave function, and so what is the implication? The implication of assigning the wave function for an electron is immediately it actually gives you the discrete values of energy. Okay, now how does this happen? You just have to do some little bit of mathematics, and the fundamental implication of assigning a wave character to fundamental particle is that their energy levels are discrete. Okay. Now we will see in a few slides how this affects our characteristics in the lower dimension. The positions within the small space is also limited. Like in the classical sense, if you say that I am confined to a small room, that means I am equally probable in every position of this room. Okay? But the rules of quantum mechanics say that there are certain places where the probability is maximum. There are certain places where probability is minimum. So that means you have restricted number of places which you can occupy in that limited space. Okay, and minimum energy is not equal to zero. We have learned in classical mechanics or Newtonian mechanics that if you can set the system in such a way that you reduce the velocity, you reduce the temperature in such a way that you can reduce the kinetic energy to zero, and you can also set the system under a zero potential in such a way that you get total energy zero. Okay? But as soon as you assign the wave function, what happens is that that zero energy concept actually takes up. So there is no case where you have zero energy. So the minimum energy what you might have is called the 0-point energy. Okay, so so that means if you think of an electron inside a small space, small electronic devices, okay, and or an electron inside an atom, that already tells you that the minimum energy is not zero. Okay. There is also a process called tunneling. Okay, so this tunneling process can only be described using the wave function or wave character of the particle. For example, the radioactive process. This can be only explained systematically using the wave character of the particle. So once you have this kind of base characters of the electron, you can actually design anything for that matter, anything in the sense a device which will behave like what you want. Okay, a particle which should give out light in such a way that, or a light emitting particle should give out a green light, means you can design it. You can design the size of this particle in such a way that it gives out green light. So it gives you a lot of opportunity for the designers or for chemists, for example, to make more and more functional materials. Okay, so the another definition, the zero-dimensional material, or you generally see that these are nanoparticles or quantum dots. What really happens in these? The electrons inside this small particles are confined to very, very small space in 3 dimensions. Okay, so that means the electron cannot move along x direction, y direction, and z direction as and when it wants. There is a restriction on this. Okay, so those are called zero-dimensional objects or quantum dots. If you prepare a wire, for example, what happens is you are allowing the electron to move along that direction of the length of the wire, but you're still restricting that electron to certain dimension perpendicular to that length of the wire and another direction, that is y and z, for example. Okay, so in this diagram, if you extend this A, for example, and forms a wire, that means this electron inside the system is freely available to move in this direction, but it is still constrained or still confined to move along B and C direction. If you can make a film, which means that the electron is free to move along 2 perpendicular directions, but it is still confined to the perpendicular direction. So these are 2-dimensional materials. So correspondingly, you have different characters, different characteristics of these 2D materials. Okay. As I said, in the case of quantum dots, the momentum and energies are discrete in all the 3 directions. In the case of nanowires and nanotubes, the momentum and energy are discrete along y and z direction, for example, and momentum and energy are continuous along x direction, because I have prepared a nanowire. Now in this direction, it behaves as a free particle, and and free particle kinetic energy is given by p squared by 2m, while the confined direction, the energy is given by something else that we will see here. Okay. In the case of thin films, for example, it is free to move along x direction, it is free to move along x to y direction, rather it is confined along z direction, so it is not able to move. So as soon as you confine here, in this direction, the energy levels are discrete. This is free here, it is defined by p squared by 2m, this is defined by p squared by 2m. So you already know that as soon as you reduce the size of the material, your available energy levels for the electrons to go are limited. Okay, if you prepare a quantum dot, for example, the number of energy levels available and the kind of energy levels available are also limited. So these are the constraints in which you work in the nanoscale electronics. So how do we solve this problem of, or how do we understand? So you confine this electron in a small space. So this is for students who have who are there, if at all there. So we confine this electron to small space, like a quantum dot, for example, or a wire, nanowire, etc., etc. So we write the Schrodinger equation, and we simplify this equation by understanding the problem in our hand, and we solve the second order differential equation, and we analyze the solution, and we get the values of momentum and energy. So all the problems in the electronics or physics is basically to understand energy of the system. Okay, so you stop at the energy of the system, and that's the reason why you get the second order differential equation. Okay, so any problem you consider is about solving the energy values or momentum values. Okay, so as I said, if you confine this particle to one dimension, for example, okay, so one dimension means this is a film, and it is not able to go along z direction, it is able to go along x and y. It is free to go along x and y. So in that case, what really happens is the energy levels are discrete. Okay, these energy levels are in terms of units of this pi square h bar square 2 square. Please remember that A is the confinement or the size of the particle you have created, or size of the film you have created in terms of thickness. Okay, M is the mass of the particle. So when we say particle, it is electron. So you substitute an electron here, electron mass here. So you get corresponding energy for various values of N. Okay, so momentum and energy are discrete. E minimum, that is not zero. Again, it is given by this 0 point energy. A lot of discussion can be done for this definitely defining the 0 point energy, but let's keep it that way and we'll move on. So now you should be able to see that when you reduce the size of the system from the bulk, let's say, to 2 dimension or 1 dimension or 0 dimension, as soon as you reduce the size, the available energy levels for electrons are limited. Available energy levels for the electrons are discrete. Okay, so we try to use these discreteness and minimum or limited number of energy levels for our benefits. Okay, so how does this look like? If you so this is extremely important for the application. Okay, so I'll just use I'll just simply analyze this equation here. It is a sine function here with this particular condition. So the wave function of this particle electron in the ground state is this way, because it's a sine, and the wave function in the first excited state is this one, the second excited state is this one. Okay, and you square that. As I said, the probability of finding the particle is square of this function. So you square this function, it gives you maximum probability at the center of the confinement space. You see what really happens here. As soon as you assign the wave function, it gives you a restricted position to be there, okay, in the ground state. So that means maximum probability is at the center of the box. While if you consider a classical particle, you can think that it can be anywhere in this space, 0 to A. Okay, equally probably it is 1 over A. In fact, the probability is 1 over A. While in the case of if you use the rules of quantum mechanics, it restricts its position. First excited state, for example, there are 2 probable positions, okay, at this place and this place. The third or the second excited state gives you the 3 possible positions, so on and so forth, depending on what number of energy levels you have. So you can actually try to think of this probability position as the position where the particle is. Okay, this is experimentally proved. You really see the electrons in that places, those positions. And if time permits, I will show you some images taken. For the ground state, for example, you see that the electrons are the particles are at the center. For the first excited state, these are at two particular positions. You can actually find out where exactly these are. And for the second excited state, there are three positions. So you really can see them from the experiment. How do you do this? This is the energy axis. Okay, the y-axis is energy axis. So that means you, in the case of an electronic device in the small scale, you can think that as applied voltage. Okay, so applied voltage can be written in terms of the energy, EV, for example. So with respect to different values of energy available for the electron, you have different positions, maximum probable positions. Okay, so I'll skip few slides here. I'll just go to application. So again, it comes back to the same slide. So now let's go to one of the very familiar application, which is information processing or information communication. Okay, so this is the light which I'm going to send. Okay, so this is the field, electric field of the light. So this is the fiber, optical fiber, for example, and this is the core of the optical fiber, and this is the cladding of the optical fibers. You send the photons here, okay, and these photons are embedded with information zeros and ones, and they travel with the velocity of light. Of course, you have to consider the refractive index of this core. Remember, this is not a free space, so it is particular medium. So that means the refractive index come into picture here. Okay, so the information is carried out in this optical fiber. Now, if you consider the ground state of this photon, now again, the photon is a particle. They will have certain energy levels because it is confined now to this space. So that means this is the ground state function. This is the first excited state function. Just like your particle in small confinement, this is the ground state function. This is the first excited state function. Okay, so same way you can define the wave function and the probability, for example. Just square that and just square this. That means you have two positions for the photons. This is one position of the photon. So if you, in the normal laboratories in our colleges, undergrad colleges or engineering colleges, the mode of transmission in the optical fiber, what we use is this one, the ground state function. And if you see the light which is coming out, will have a spherical circular shape. Okay, the light which is coming out will have a circular shape. How do you know? You just make a line scan here, plot the intensity, and you will find something like this. Okay, now if you want to transmit the information in the ground state, that means you will be able to send only one set of information. That means, let's say you want to send the text, which is converted into zeros and ones. So that means if you are just particular about sending a text from one place to another, you can use the ground state of the photons. If you want to send the information, like for example, the text and the image, if you want to send together, then what you do is you send it in these different mode. Okay, so this is called mode of transmission. This is the ground state, fundamental mode. This is the first mode, TE1 it is called. So that means you can send the text information, which is in this spot, and you can send the image information, which is again converted into zeros and ones, in fact, okay, in this spot. If you see the first excited spot, you will have the emitted light will have two spots, two separate spots, and in one spot you can send the text information. In another one, you can send image information, and that is the exact reason why, over the period of a couple of decades, the speed in which we have been able to transmit the signals, information is becoming faster and faster. That means more and more information is available at same instant of time. For example, now what I'm speaking, that means there is a voice which is converted into zeros and ones. There is image which is also converted into zeros and ones, and this is transmitting. Earlier, it used to be only voice transmission, so that you needed only the ground state. Okay. Now, since you have this multi-mode, you can think of the second excited state here, and you can see that there will be 3, there will be 4 spots, and you can use multi-mode transmission. And the way in which it works is exactly similar to the particle confinement. Okay, the ground state wave function, the first excited state wave function, the second excited, and so on and so forth. So depending on how many information or what sort of information you want to send, you can choose different modes of transmission. So this is one of the beautiful example or beautiful application of the confinement problem, confinement of a particle in a box. Okay, so now where is the confinement? The confinement is basically the light is confined to this small space, which is the core of the optical fiber. Okay, and the light which is coming here, if you are very good in transmitting the signal along the axis of the fiber, then it is absolutely fine. If not, let's say you are incidenting or making the light to go through here in this particular angle, it will be refracted. It will be refracted like this. There are total internal reflection, so on and so forth. But again, it is carefully chosen core and cladding material, so obviously it will go through. It will undergo total internal reflection, and you have the ground state and the excited state depending on what sort of information you want to transmit. So this is one of the best example you can give when you discuss the particle in a small confinement. Okay. Now another one application is the design of the light emitting diode. Light emitting diode is simply PN junctions. Okay, P-type material, N-type material, and they are sandwiched in such a way that it forms a PN junction. And depending on the material you choose, you can actually make them emit light, and that's what it is, light emitting diodes. Okay, so for example, if you want to have a UV light emitted by the LED, you have to design it in such a way that the energy of the semiconductor should be 3.25 electron volts. And all the LEDs what you buy in these markets these days are basically the LEDs in such a way that the PN junctions are sort of quantum wells. That means these are two-dimensional films of P-type material and N-type material deposited on a substrate, and they design this light emitting. And in fact, please remember that we might think that, oh, okay, it is just a PN junction. Okay, but please remember the history of designing the PN junctions and blue light emitting diode. In fact, I think 2011, the people who designed blue LED got Nobel Prize. So it is not a very, very simple concept of designing LED. Okay, now why do we need the green, blue, and red? So it is basically, it's not just about the technical aspects of this light emission or scientific aspects of light emission, but if you combine this green, red, and blue RGB, for example, you can create white light. Okay, so there are huge amount of applications involved. And please remember that designing and successful design of blue LED took about 30 years, even more, while red and green was already available during 1960s. Okay, so most of the time we use gallium arsenide to design the light emitting diodes. Please remember, these are small. These are in the form of films, thin films of certain thickness. So that means electrons in these materials are confined to small space, and they form the junction, and they give out light. If you apply a proper bias, they give out light. So there is electron recombination taking place, and the energy difference is given out in terms of light. Okay, so red light, for example, if you want to have a red light which is about 620 to 750 nanometers, you need to have energy gap of 1.8 to 1 electron volts. Okay, most of the time, or all the time, the LEDs are designed using the gallium arsenide. Intrinsic energy gap of gallium arsenide is 1.42 electron volts. So this is not too far. That is about 0.4 electron volts. That means if I want to have a red light emitted by a gallium arsenide LED, we somehow have to manufacture a PN junction using gallium arsenide in such a way that you get an energy gap of 1.81 electron volts, and correspondingly, if you can make the electron and the hole recombine, that can give out red light. So this was done during 40, 50 years back. Green light, you see, for example, the wavelength region is about 495 to 70, and it is 2.38. Still, it is fairly close by. You can manage it by alloying this gallium arsenide by certain elements. I'll show you one table at the end of the presentation, how they do this. These people could do this, red and green. Look at this blue. If you want to have a blue light from gallium arsenide LED or a junction, for example, the blue light has a wavelength range of 450 to 495. That means the energy gap between the conduction band and valence band should be about 2.6 electron volts. From 1.4 electron volts to 2.6, it's not that easy to manipulate these energy gaps. Okay, so a lot of effort needed for researchers to design this material in such a way that it gives you an energy gap of around 2.6, and then they get so once you have these three colors, and obviously then the engineering part comes, how do you mix these three lights together to get a light? Okay, so fundamentally the design of light emitting diodes is also one of the very interesting and much involved research work, and currently in my group we are trying to design this light emitting diodes by using low dimensional materials. Okay, low dimensional material is not like you deposit thin film and design the LED, but we really prepare these materials in lower dimension, like 1 dimension or 2 dimension, and check if we can design a LED. So this is just for your information. I'll just skip this. What really happens in the case of confinement, that you apply, so this is PN junction, for example, there is a quantum well. Quantum well basically means there is a confinement space between these two materials, and by properly applying bias voltage, what you can do is you can collect the holes here, you can collect the electrons on this, and at one moment of time, this so many number of electrons collected in the bottom of the conduction band and top of the valence band, these holes can be recombined, thus giving rise to a very high intensity light emission. Okay, so this is the principle in which LED can be designed. This is also the principle in which quantum lasers are defined. Okay, the only difference is in the process in which the recombination happens. In the case of light emitting diode, it is simple light emitting diode. It is just a spontaneous emission taking place. But in the case of lasers, the quantum lasers actually induce this transition or recombination. Okay? So you can use some simple pictures like this. For example, there are quantum wells here, quantum wells, and confinement. So there are discrete energy levels. Okay, by apply a certain bias voltage at the true end, what you can do is you inject this electron to this one, this quantum well, and obviously the only place it can go is this energy level inside the quantum well, and the difference of energy is given out in terms of light. Now this electron, which is recombined, can go to the next quantum well, and again it is well defined with the two energy levels, and it gives out the light. So if you can manufacture these small quantum wells, when I say quantum wells, means industry manufactures these quantum wells of thickness about 10 nanometers. Okay, so electrons are confined to that small space, and you can calculate what are the energy levels and what is the transition this electron can have, and what is the light which can be emitted using this this kind of manufacturing system. Okay, you can also design a transistor. When I say transistor, means it is a field effect transistor. So here is the scanning electron microscope image of a field effect transistor. Okay, And so you can refer this in 2012 paper. So these are the channels. These are channels here, and this is the source, this is the drain, and here are the gate electrodes. So these are the source, these are the drain, and you can actually define or design this kind of transistors, and you can embed them into larger electronics. So in fact, this group has manufactured these kind of transistors in 1 centimeter by 1 centimeter chip, silicon chip. That means similar transistors are there. I mean, I think more than 100 silicon, 100 transistors are there in that. We characterize them. Okay, so it is possible, and this is the sort of side view of the same transistor. So you have the source, you have the source, you have the drain here, and then correspondingly this wire here, this wire, which is the channel, for example. Okay, so you can design and you can fabricate this. The only limitation is that you have to have optimum control over your material you are preparing. You should know exactly what are the properties of these materials, and you should know exactly how to assemble these electronic devices, and you also should know how to characterize them. As soon as these dimensions go below, let's say 250 nanometers, your normal optical microscopes are not sufficient to see them, okay, because your resolution is not sufficient to see these materials at small scale. You use scanning electron microscopes, okay. So the electron microscopes, you can see the materials up to about 10 to 15 nanometers, okay. But it is possible that your nanowire here is about 5 nanometers. So how do you see this? Okay. There are certain experiments you can do, like for example, scanning tunneling microscopes, scanning tunneling microscope, which is called STM, and you can also do a transmission electron microscope. So there are equipments available in different labs or various labs, various institutes, where you can really see them and you can manipulate. So please remember, the first question I posed is see the material at the nanoscale and have a capability to manipulate them as and when you require. So we do have equipments and instruments to do things at small scale. Okay, you can do simple surface science, for example. There are no applications involved, but you can just see how molecules adsorb on a surface and how do they organize themselves. For example, this is one scanning STM image of a carbon monoxide molecule, as shown here. Okay, the way in which it adsorbs on a copper surface is oxygen protruding out, and carbon atom actually sits on the copper surface. So you can do beautiful science. Need not be every time. It need not be application. You can really do some fundamental science at a small scale. Okay, and see this. These are experimentally observed images. For example, this is a particular molecule. This is using an instrument called AFM. And so it is possible to see these materials or molecules or atoms at their fundamental level. Okay, molecules you see assembled on the surface, and this image really see or really gives you an idea how this ball and stick model came up in the early 50s. Okay, so we always written or wrote the chemical formula of any molecule, for example, using ball and stick model. And if you use AFM, for example, you do see them as a ball and stick. Of course, the balls you have to imagine, but you can imagine the sticks. The sticks or the lines are bonds between the atoms. And so these days you have instruments to do almost everything in the nanoscale. Okay, and I was really happy to do things at this level, and we have done some wonderful work. There are also people who actually want to do things at molecular scale level, which is a single molecular level. So the idea is simply you design a molecule with the very specific characteristics and connect it to clips, crocodile clips, for example, apply a voltage and measure the current. Okay? So this is one single molecule device. whether it behaves as a simple switch, for example, or not. So it depends on what sort of characterization you get of IV characteristic. Ultimately, what you measure is the current going through the system. Okay, so these you can gate them, etc., etc. So there was a program which I participated a few years back, where we wanted to fabricate a single molecule logic device. And please remember that this is about, so it is 1, 2, 3, 4. So that means it is 0.2 times 0.8. It's, let's say, 1 nanometer arm. Okay. So this is 1 nanometer arm. This is 1 nanometer arm. This is 1 nanometer. And I need to get the logic operation using this molecule. Okay. There were collaborators who designed this molecule in such a way that computationally you know exactly this is the operation you will get if you do the experiment. So they will say this computationally. So our job was to really fabricate them on the surface. So this is a silicon surface, and so we try to measure them. So we can have a source, we can have a drain, we can actually gate, or we can use this as source and drain, we can gate them. So there are instruments available in the world where people can do things at a very, very fundamental scale. Okay, I'll skip this. This is more of science and mathematics, so I will not bore you with all these things. So this was the instrument which we used for measuring the logic device at single molecule level. And of course, since the active part of this device is one single molecule, we needed expertise of electronics, we needed expertise of physics, we need how to assemble them on a surface. So there were a lot of expertise. Okay, so we were successful. So as I said, there are characterization techniques available for you to use to understand the materials at small scale. For example, electron microscopes. As I said, transmission electron microscope uses electrons, high energy electrons, and you can get really the atomic arrangement on the electron microscope, for example, scanning electron microscopes, again use the electrons. The energy range is slightly lower than the transmission electron microscope. This is actually low energy electron microscope. It is called NEEB. Here we use very, very small energies like few electron volts. So these are all microscopes which you use or which we use to see how the material, how clean is the material, how the atomic arrangements inside the material, etc. In fact, in VIT, we do have a TEM, we do have ICM. If anybody wants to have some sample analysis done, please contact me. There are certain other electron techniques which use electrons, but they do not directly see the system like atoms or molecules, but they give you an indication of the organization of these atoms and molecules by using the diffraction pattern. Okay, so electron diffraction, again, the wave character of electron is used here. So this is reflective high energy electron diffraction. Okay, so we use electron energy of about few kilovolts, 5 kilovolts or 10 kilovolts, and we make them to incident on a shallow angle to the subsurface, and we see the diffraction pattern. Similarly, this is low energy electron diffraction. This is energy loss spectroscopy. Again, all those are used using electrons. The fundamental idea behind using electrons is that you can tune the wavelength of these electrons. Okay, you are not able to tune the wavelength of the photons for that matter. Okay, you are restricted in terms of tuning the wavelength of the photons, but rather in the case of matter particle like electrons, you have complete freedom to tune the wavelength. So again, go back to our lambda is h divided by the momentum p. Okay, so and again you had the square root of 2 e. E is the energy we give it to the electrons. So very, very high energy means smaller wavelength. Smaller wavelength corresponds to smaller entities you can check. Okay, and these are low energy electrons. So that means the energy is very small. So it is square root of energy in the denominator. That means the wavelength is larger. So that means you can see the broad picture of the surface on the microscope. Okay. Similarly, you can tune these wavelength of the electrons, so you can choose experimental techniques what you want to have. So since now my program coordinator tells me that there are 3 minutes, I will skip. So if somebody wants to have the slides, I will just share it. Recently, I started working with one professor in the university about nanoscale material in biology. Okay. So this is a surface of eye of a moth. Okay. So here there are nanostructures organized hexagonally, and there are some domains, and we are trying to understand how the eye of a butterfly or eye of a moth works. Okay, so again, you can use the principle of or principles of physics, for example, try to understand the regular pattern. You do use some crystallography principles and try to understand how the optics works. Okay. Okay, so there is again one more direction in which you can go is to understand how the chemical reaction happens in large molecules inside our human body. So this is our DNA, for example, and DNA is connected with these molecules. I'm not worried about what molecule it is, but one thing recently people have found is the way in which gene mutation takes place is because of the quantum tunneling of the protein. Okay, so this is the central part of this gene here. I'm just considering one small part of this molecule here, and you can see this white dot here. Okay, these are protons, these are hydrogen. Okay, and the distance between this molecule, the T molecule, and A molecule, this is basically ATGC. Okay, A and T. Okay, so the distance between these two is 0.181 nanometers. That is like 1 extra units. So the space in which this proton is 1.8 angstrom. So from the rules of quantum mechanics, it always tells me that this proton can actually tunnel through the other side. Okay, so that means proton can break here and it can go here. This is exactly what happens here. Okay, so this is the intermediate state and this is the final state. So the proton which was on the opposite side now has become the place changed or location changed, and people say from the chemistry background or biology, they say that gene is mutated. Okay, so the physics at small scale is not just restricted to optics and electronics. Okay, it is also now expanding or trying to put his feet in the biology, trying to understand how things work in the biomolecules. And recently there was also another study done on how exactly the photosynthesis happens using the principles of quantum mechanics. As you know, the photosynthesis is basically a process where light in the form of photon hits a leaf, and there are certain reactions taking place, and there are reaction centers, and where oxygen is involved or oxygen is given out, thus creating the energy. Okay, so till now, chemists and biologists were satisfied with the chemistry part of it. That means they thought that everything is explained under chemistry. Okay, but now some people are trying what is responsible for this chemistry principle in photosynthesis, and they found that it is actually a photon which hits the molecule on a leaf and immediately shows up its wave character. Okay, and just imagine that it is the photon is hitting the leaf, the pigment, and where actually it shows up its wave character and distributes itself in the space available in such a way that it chooses the easiest path to go to the reaction center, and the reaction takes place and the oxygen is evolved, given out, etc., etc. So the fundamental mechanism in which this happens is the photon tunneling. Okay, so if somebody is interested, I will also I will send you the research work done, and these are all topics under quantum biology. It is recently developed in science. People who are interested, please go to internet resources, quantum biology. It's a wonderful subject. Okay. Yeah, so to conclude, materials and matter at low dimension is really a playground for physicists. because there are ample opportunity to find out newer physics, newer phenomena, and ample opportunity to convince the engineers that you can design something new devices. Okay. Of course, you have to know the dimensionality of these devices and materials. And we have reached a stage where we can controllably create the materials in the sense of quantum dots, for example, in the sense of molecular machines. And we are stepping into a regime where in few years we might be talking about atomic scale electronics and quantum computation. So with that, I will stop, and I thank you very much for patient listening, and I'm ready to take a few questions.
Yeah, thank you very much, Dr. Ramesh. It has been a wonderful session for us. Now let us take up some questions.
Yes, please. Yeah.
One question is regarding the quantum algorithm. What extent this quantum algorithm is true? Whether how long it will take down the line?
So I think the question is related to quantum computation, right? So basically what we do in quantum computation is, let's say we have to know the difference between classical computation and quantum computation. In classical computation, what we do is we have zeros and ones, and this device can show either 0 or 1. Okay. So that means it is either off or on. Please remember, I'm using or. The word or, it is very extremely important. So it can be either on or off. It can be either 1 or 0. In the case of quantum computation, what we do is we actually use the rules of quantum mechanics. I did not show you the rules, what are the rules, but there is something called superposition of these zeros and ones. Okay, so that means since the electron behaves as a wave, this wave now can be in a superposition state. Now this superposition is defined by rules of mathematics. How many states are available for the superposition is defined by rules of mathematics. So that means you have these so many states available apart from zeros and ones. And that is the reason why, if you can actually put the electron in a superposition state, you can do computation much faster and much efficiently. And so people have tried with the various ways to prepare these superposition states. So fundamentally, this is called a qubit. You need to make this qubit available in a superposition state, and then manipulate, then start computation. Okay, so right now it is under the theoretical framework. Everybody is saying this is possible, but only few quantum computers are available, and one is the IBM's computer available for us to access, and there are very few research work published on this direction. So it will take a decade for that matter to really establish us, to really see that we can use quantum computation for understanding few of the unsolved mysteries of nature.
Okay, any other questions? If there are no questions, we'll wind up this session. I thank Dr. Ramesh Thamankar. Sir, thank you very much for your very valuable insight into the topic. We are grateful to you on behalf of the college and our Department of Physics.
If you allow me 1 minute.
Yes.
Okay. This is for all the listeners and everybody. Okay. This is actually the numbers, everyday numbers in India on COVID. Okay. I want to remind every listener that this Y scale is in log scale. So this is in logarithmic scale, and this is the number of days. I have data points here also, but please remember that this is linear in logarithmic scale. That means it is exponential. The last data point is yesterday's. So please do take this very seriously. We are climbing the exponential growth of number of cases detected, and we haven't reached the maximum of the exponential growth. So please be safe, take care of your family and take care of your friends. Avoid the get-togethers for at least time being. Okay. So this is the message I wanted to give you. Please.
Yes, thank you, sir. Thank you very much. Thank you once again, Dr. Ramesh Thamankar. It is very much appreciated that you have been here for our webinar. Thank you very much.
Yeah.
I thank our management, our principal, Dr. Vio, and Dr. Vincent, the HOD of our department, all staff members for their full support. Thank you very much. I also thank Mr. Ragesh for his continuous technical support. Thank you very much. Thank you all. Thank you all the participants. Thank you very much.
Hello.
Hello.
Namaskara.